Hello there, I'm Sriram, Ganapathy, a faculty in the electrical engineering and director of the learning and extraction of acoustic patterns, the LEAP lab. So we founded the lab a couple of years ago with the goal of trying to understand and analyze acoustic patterns. Acoustic patterns refers to speech signals, audio signals, and patterns that can be either derived from the signals or that are simulated by these kind of signals. So understanding like acoustic signals and patterns in acoustic signals propels fundamental science in signal processing, in machine learning, in auditory neuroscience, in human behavioral science and psychology, and a lot of other fields. So it's a very interdisciplinary field that we try to focus here and try to advance these areas in conjunction with analyzing acoustic patterns. So we as a group, we started with one PhD student, a master's student, and a very small group of interns. But now I think in the last couple of years we have grown quite a bit in terms of number of students. We have a vibrant group of about 15 students now, with PhD students, postdoctoral fellow, master's students, project students, and so on. We have basically been blessed with good students in the sense that whoever the project students who have graduated have secured top higher studies in top US universities. They have master students who have graduated have secured high-paying jobs in various industries, both in campus placements and outside. So the group as such, whoever has been part of the group seems to be doing well, which is a very good sign that we are doing something right. So in terms of the work, we have a variety of disciplines that we focus on. We have signal processing, noise robustness, speech recognition work, which involves deep learning and machine learning aspects, speaker and language recognition and modeling, some amount of accent modeling, and speaker diarization and clustering. Then we also have a group of people working on neuroscience side of speech production and speech hearing, and also in learning new languages. Then of course we also deal with human behavioral data, how humans are able to pass information like speaker and language by conducting experiments with human subjects. We work with various collaborators, both nationally and internationally. We have collaborations with NIT Suratgarh, with IIT Bombay as national institutes in India, and of course with international places like École Normale Supérieure and also Carnegie Mellon University in the USA. Have a postdoctoral fellow which we share with CMU, who spends half the time here and half the time there. And in terms of agencies of government which we work with the DRDO, the ISRO, and also in various initiatives with the Department of Science and Technology, the DST. And in terms of industry, we collaborate with the startups as well as big industries in audio and speech processing, and as well as in the areas of broadly machine learning. So I would like to think that we are a vibrant group of people who try to work on cutting-edge technologies and push the frontiers in science and technology. We try to advance the state of the art, participate in various challenges both of academic interest as well as for national and goal-oriented projects. So this kind of advances the field, propels us to move and innovate new technologies, and also develop systems that can solve real-life problems.
Hi, I am Sriram. I am a postdoc fellow in LEAP lab. I joined LEAP lab in 2017, and with me I have my team member.
I'm Shobna, and I'm a project assistant in this lab, and I've been working here for about a year now.
So together we are analyzing conversational speech data sets so as to analyze how humans do different tasks while listening to conversational speech in day-to-day activity, and how machines perform when they work with these data sets.
Machines are typically very dependent on the type of data set it receives. Currently, data sets such as meetings data and child data is not very well analyzed, and it does not do very well when you work with these machine systems. So we need to build better systems for these kind of data.
Yeah, and humans are quite good at these tasks. Like we can listen to a speech when two speakers are talking, and we can focus on the speaker we are interested in very easily, and the other voice goes to the background quite nicely. So machines have not reached that sort of performance which humans have in such data sets. So how we are approaching this problem in GitLab is we are performing listening tests in which we have designed our own data set by collecting conversational speech recordings, and we make humans listen to these recordings and answer some questions while they are listening to these recordings. And one of the question we ask is how fast do humans detect speaker change? So generally responding to light is quite fast, and also mechanical responses are quite fast. So we are interested how fast humans detect speaker change while listening to speech. And parallelly, we are also doing the
machine side experiments. So when we have to look at it from a machine's perspective, the machine has to listen to this audio piece by piece, and so it keeps progressively listening to this audio, and it starts extracting certain features from this audio. These features are encoded as numbers, and these numbers are compared with each other, and accordingly the machine will decide whether there is a speaker change or there isn't.
Yeah, exactly. And with the speaker change detection task, though looks very fundamental, but machines have a hard time doing that, and the reaction time of machine is also not very high. So we are trying to see how good machines are and how good humans are, and can we match up the performance of one to the other, and eventually we want machine to perform better than humans, so that some of the tasks, the repetitive tasks of humans while analyzing such recording gets less tedious. So hopefully we'll have more updates to share with you all. Stay tuned.
Hi, I am Sriram. I am a PhD student in Lead Lab. So here we were having a discussion with my teammates.
Incho, Madhavan.
So when I am talking to you or when you are listening to what I am speaking, our brain is also playing an active role along with our sensory organs. So here in Lead Lab, our group is trying to understand how the speech is encoded in our brain. So or we are trying to understand the neural processing of speech sequence. So as a first step towards it, we recorded EEG signals from human subjects when they were performing speech production and perception tasks, and they were listening to two languages. One was English and the other was Japanese. And English was?
So English was known to all the subjects as we picked the subjects from around our campus, and Japanese are unknown to them. So we used a 32 channel EEG cap, which is gel based, to record our data, and we did it like we had 3 stages while recording. One, the first one, when subject will listen to the word, suppose we are saying good, and then in the next cue, subject has to utter the word in mind, and in the third cue, he or she has to speak it out. It's just like the natural way of learning a new language or a new word. When you listen to a new word, we try to utter it in mind after listening to it to gain some confidence, and then only we speak it out, right? So the same way where we have tried to get our data, and we are trying to analyze the things and try to understand how human perception is about the known language and while learning a new language and all these things.
So our work has basically 3 directions. One of them is we try to classify which word they are listening. During the first phase, when they are listening to a word, each recorder signals are recorded when they listen to both English and Japanese. So using the techniques of machine learning, we try to declassify them. So whether we are hearing an English word or a Japanese word. The second one is to build a language model of the words spoken by them. So with due course of time, when the stimuli are being presented rapidly, multiple times, we would like to see if the way the subject is pronouncing the word changes over time, and whether this change over time is being recorded in the EEG signals as well. We would like to see whether there is a relationship between the EEG signals recorded and the audio spoken. And the third phase is to see how an unfamiliar word changes in the representation of the word in the brain. So for this, we try to build a filter which maps the relationship between EEG and audio, and then we try to see how it changes over time. So presently, we see that with change in time, the subject builds a better representation in the brain. So the future course of work in our work is
So further, we would like to see, we want to show that whether we can predict what language the person said from when he was listening to the one particular word, and also we would like to show that there is a correlation between what we heard to what we spoke at the later stage. So these are some of the interesting work we are doing as part of the auditory neuroscience and the combination of auditory neuroscience, machine learning, and signals. Thank you.
Thank you.
I'm Purvi Agrawal. I'm a PhD student in Leap Lab under Dr. Sriram in the Electrical Engineering Department. So so I would like to give a brief. I would like to brief about the work that we are trying to carry out in the lab. So the thing that we are trying to achieve is we want to make a speech recognition system which is robust to noises, real-time noises that we face in our real day-to-day life. So we know all these speech recognition products that are already there in the market, like Siri, Cortana, Echo, which interact with humans and tries to do the conversation by understanding what humans are saying and then replying at the same time. But we also know that these systems don't really work well in the presence of noises, like let's say we are in a restaurant, or we are sitting in a train, car, we are at a traffic signal, or be it any kind of noisy environment we face in our life. So we are trying to build up some such system that can deal with the noisy backgrounds. So the motivation of carrying out the work was that humans are able to do the speech recognition in presence of noise, but we haven't got that accuracy yet in the machine. So what if we can understand what goes on in the human brain to understand and listen to the speech signal, and what if we can replicate the same thing into the machine to build speech recognition system. So according to auditory neuroscience studies, it is hypothesized that when a speech signal enters the human ear, the speech signal passes through the neuron architecture to the primary auditory cortex, and during the passage through the auditory pathway, this signal gets filtered out, and it just retains the relevant information which is necessary, and it just filters out all the background noises which are not important for speech recognition. So, and this type of learning, this type of filtering process inside the human brain is completely autonomous. Like, we do not train humans to do that. Humans learn, and humans get adapted to these type of environments and listening in such type of environments as and when they get more and more exposure. So we want to replicate such type of filtering process in a speech recognition system. So in speech recognition system nowadays, what we typically do is we feed the speech signal features, we extract useful features from the speech signal, we feed those features to the deep network, we train it, and we get the output. But when we extract those features, can we make those features more and more robust to noise? Because whenever the speech signal is noisy, we can see the impact of the presence of noise into that feature which we are feeding to the network to train. So what if we can filter out that feature? How we can make that feature more and more robust to noise? So in our work, since we want to do this learning process without any supervision, we want the system to learn such type of filters on its own without any external supervision. So for that, we are trying to do unsupervised learning. So in this unsupervised learning of filters, we are making use of a generative model. So in the generative model, it tries to learn the input data distribution, and through this learning procedure, we get a filter which when we applied it to the features and trained SR with that, we saw that it led to a huge improvement in the SR performance, and we interpreted that this filter
filter is retaining only the relevant information and filtered out the other types of noises. So we do this learning process of filter through a large amount of speech data, and when we learn the filters through a large amount of speech data, we hypothesize that the common underlying representation in the huge amount of speech data is the speech content, which is common. The rest of the background keeps on changing in different speech patterns. So that's why we interpreted that because of such type of learning process, when we learn the input data distribution without any aid and then putting those filter features to train a deep neural network, it tries to mimic what is happening in the human auditory processing. In the near future, we would like to extend this work for Indian users where we have multiple languages and multiple accents. And the current systems that we have right now in India, they deal with a lot of problems because of the heterogeneous speaker population that use such products. So, whereas humans are able to communicate with each other even in such diverse multilingual environment. So, we hope that we should be able to make such system that achieve the same accuracy as how humans communicate.
So, how's your experience in the lab?
Okay, so experience in lab is awesome. Like we work, we have fun, we party, and yeah, it's really good. We get to interact with a lot of other people of different domains, and we learn a lot from each other. We all work together, so it's very good.
Hi, I'm Shreyas, PhD student in Deep Lab.
I'm Satish Kumar, I'm a project associate here.
My name is Vaishnavi. I work as a project assistant here.
I'm Bharat and I'm a master's student here.
So the project that we are working on is language identification. So our broad area of research is speaker and language identification. As the name suggests, what we are trying to achieve is that when we give a speech recording as a prompt to a computer, it has to automatically recognize who spoke and what language was the speech spoken in.
So, this problem of spoken language identification, we are using techniques right from signal processing to statistical modeling to deep learning. And the main problem is when the languages are dialects of the languages themselves. Like you have English medium, English American, and continental Spanish, European Spanish. The problem becomes difficult there. The system will struggle when there are dialects that are very close. And another problem is when the speech interval is very small, like 1 second, 2 seconds, 3 seconds. So each of us are trying to solve these problems separately. Some of them together, and yeah, we have some good results, and yeah, we are moving forward in that direction.
To extend that project, we are trying to develop a complete system for speaker profiling, like apart from language, accent, dialects, and so we are going to include weight, age, and height also. So you can think of this application of that system, like suppose a system is trained on that data set, and we are also going to collect data for Indian languages also, like 10 to 12 Indian languages. So you can think of a system, it's already trained, and you can put a system somewhere. Suppose you are from Tamil background or from Kannada background, you go somewhere like Bengal or Assam. So if you fail in some trouble, so our system will be like, suppose you call someone, if he don't know your language, so if the system is already there, so that system will forward your call based on your accented speech or your native speech to the concerned person, and they will be able to help you immediately.
So, where is this language recognition used? It's used as a front end to a speech recognition system. You have different speech recognition systems which are trained for specific languages. Say, a speech recognition system to recognize only English, or maybe to recognize only Hindi language, and so on. So, we can use this language identification system as a front end to recognize which language we are speaking, and based on this recognition, we can give it to that respective speech model.
Also, if we use speaker and accent identification here in ASR applications, we can adapt the ASR models to that particular accent as well as that particular speaker. So, so as to improve the performance of the ASR also.
Thank you.
Hello, I'm Sonali. I'm an MTech second year student in the Department of Electrical Engineering. My program is System Science and Automation. I'm a member of LEAP Lab for the past 1 year. I'm working under Dr. Sriram Ganapathy, and my project is to do unsupervised acoustic modeling in zero resource settings. So in machine learning, we know that we can do unsupervised learning or supervised learning. Basically, we see that in speech domain, we do a lot of, we have already experimented with a lot of supervised stuff where all lexicons, gender information, speaker information is incorporated in ASR, automatic speech recognition. But suddenly, as we see that there are many languages for which no such information is available, and the interest is shifted to how robots acquire knowledge or how the infants acquire knowledge. So to understand that, many people have started with unsupervised speech recognition. Recently, a challenge was posed called the Zero Speech Challenge. The whole goal was to do unsupervised speech recognition for some low resource languages like Mandarin. So we as a team from the lab participated in that, and as one of the problems was to do unsupervised acoustic modeling. So by acoustic modeling, we that to discover frame-wise better feature representations as compared to NFCC. So we did some GNM based clustering to discover some new features which perform well. Also, the goal in unsupervised word clustering is to do full coverage, segmentation, and clustering. That we need to discover all the boundaries of possible words without the availability of lexicons or dictionaries. So, in the tracking of the problem, we have done somewhat good work, but still I'm doing our tracking to try to discover full coverage and segmentation. Application of the rules and concepts supervised clustering and unsupervised speech recognition low resource languages. Also, we can learn how robots acquire language via speech language. Also, this whole stuff will give us some new insights in speech processing. Thank you.
Hi, my name is Arif, and I am an MTech second year student of signal processing. So I've been attached to this lab for the past 1 year, and the problem that I've been working on is called as speech diarization. The problem of speech diarization can be introduced by taking a simple example of a man speaking into a microphone with the microphone in his hand. So suppose the microphone is near to his mouth, and as the person speaks, the energy that comes from out of his mouth is going to impinge on the mic, primarily from a direct path from his mouth to the mic. Now suppose the mic is kept further and further away from his mouth. What then happens is that you start to get what is called as reverberant energy, also in addition to the direct path. Now, when I say reverberant energy, what that means is that the energy that is being reflected off from the boundaries of the room, such as the floor, the ceiling, and the boundaries of the wall, or even any object in the room. So, when that happens, we have a lot of problems in recorded speech. So, basically what happens is that machines have a hard time understanding
impairment, they also have a hard time trying to understand the speech. So this is a very real and significant problem, and this is not an old problem at all. This has been looked upon by researchers for many years, over many decades. But it is still a very live problem. Researchers always come up with many new techniques. We are also trying to find out many new different ways to try to hear the brain speech. So one of the methods that we have been trying to look upon is by trying to make use of machine learning itself in a supervised setting to do de-regulation. And by that what I mean is we train a machine with a lot of examples of appropriate speech and clean speech and try to make that machine learn a particular mapping from the appropriate speech to clean speech. And so when a new appropriate speech segment comes, the machine hopefully will be capable of mapping it out to clean speech. So this is very interesting because we just have all that we need to have is just a sufficient amount of data of both appropriate speech and clean speech. And then the machine does its work. It works its magic. So we're trying to look on that line. Another approach that we've been trying to work on is based on traditional signal processing methods. Specifically, we're trying to use linear prediction, what is called as linear prediction, to estimate the appropriate energy components in the speech signal and then subtract it out from the input signal. And then say that there is certain signal is going to be de-regulated speech. So these are both very interesting, and from the primary results that we have been having, it seems that we are taking the right direction. So let's see where it goes.